From Photonics Media, this is All Things Photonics, a podcast shedding light on industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts speak with luminaries, rising stars, and market leaders about the trends shaping the current and future landscape of photonics. From space and deep-sea exploration to precision timekeeping and advanced manufacturing, this is the podcast for progress on All Things Photonics. This season of All Things Photonics is brought to you by Poly Science and Thor Labs.
Today's episode is brought to you by PolyScience. For over 60 years, the PolyScience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's a part of our history. Today's episode is also brought to you by Thor Labs, a global designer and manufacturer of photonics technologies. We provide a comprehensive portfolio of over 22,000 stocked items for same-day shipment, complemented by endless custom solutions enabled by our vertical integration. Visit thorlabs.com to learn more.
In today's episode of All Things Photonics, we'll be speaking with two leading startups working in very different technology spaces. The first is Lightwave Logic, a company developing electro-optic polymers that allow data to be transmitted at higher speeds using less power and in a smaller form factor. The technology promises to address key bottlenecks and hurdles faced by the data center and artificial intelligence industries. The second is Tau Systems, a company that's made it possible to significantly shrink down particle accelerators to enable research work that was previously only done by scheduling time at a handful of properly equipped facilities. While the companies themselves are fairly young, they're backed by seasoned and accomplished technologists. Michael Lebby, CEO of Lightwave Logic, is a Bell Labs alum and an expert in semiconductors and optoelectronics. He's led several deep tech startups, as well as groups and companies like Motorola, AT&T, and Intel. In today's conversation, we'll discuss Lightwave Logic's key innovations in the company's path to commercialization. Steven Milton, Vice President of Accelerator Science at Tau Systems, another Bell Labs alum, is an international leader in the science and technology of particle accelerators and free electron lasers. Notable resume lines include Argonne National Laboratory, the Advanced Photon Source, Brookhaven National Laboratory, and others. Today's conversation looks at key advances underpinning Tau Systems' achievement in miniaturizing what have traditionally been massive machines requiring entire facilities, their near-term uses, and what these devices mean for the future of research. But first, here's news editor Joel Williams speaking with Michael Lebby, CEO of Lightwave Logic. For those in our audience who aren't familiar with your company, could you give us sort of a brief overview of Lightwave Logic? What technologies are you working with, and what problems are you trying to solve with them?
So the company Lightwave Logic, I joined back in 2015. It's a Denver-based company in Englewood, just south of the tech center, Colorado. And the company's been around for about a decade or more, developing electro-optic polymers. So these are polymers where you can apply a voltage or a field or a bias, and you can create a change in refractive index, optical refractive index. And so if you do this in a modulator type scenario, you can actually switch light. And so we design our materials to go into modulators. So the company has really got its roots as a chemistry company. And the original founders came out of DuPont in Delaware. They're not with us anymore, but what they did was they set up the company, and we've really enhanced and fine-tuned the chemistry so it actually performs really nicely for data center type applications. But really, as a chemistry company, the company was fortunate in about 2008. Actually, as a chemistry company, went public on the small boards, the over-the-market OTC type public boards. And then in 2021, we made enough progress and enough interest and generated enough technical development towards using our electro-optic polymers into modulators that actually we went up to the NASDAQ. And so we're a NASDAQ public company. We're still essentially pre-revenue. We don't have any debts. I mean, you can look at all our data. It's NASDAQ LWLG. And as a public company, we're sort of in a startup type mode, advancing this technology platform. And the electro-optic polymers, you have to look at this as the industry itself. If you think about the modulator industry, that modulators are used in their millions, in the optical network or the internet, and they're generally placed right in front of lasers. And so if your laser sending light out into the fiber, modulator essentially just modulates the light. Now, we knew 10, 15 years ago that lasers directly modulated had real trouble turning it off quickly. So now we use a modulator to help the laser do that. And the interesting thing about using polymers as opposed to semiconductors, because today, if you look at a modulator incumbent technology in the optical network, it's either indium phosphide or it's silicon. There used to be a lot of lithium niobate modulators early on, 20 years ago for the telecom. And that's really sort of morphed into thin film lithium niobate, which is being developed today. There is great demands today to have high speed, low power optical modulators. And it just so happens that Mother Nature really works with the chemistry and the polymer material. And so we have a technology platform that has really nice performance when you design it into an optical modulator.
I'd like to go a little bit more in depth about that, about your platform and sort of what makes it unique. Can you tell us about some of the promises and the benefits of electro-optical polymers?
Yeah. So the first thing you want to think about is it's not a semiconductor. So it's polymer based. And what we actually do here in Colorado is we create the chemistry, our own chromophores. So, it's a technology that you can integrate into a silicon process. But at the very highest level, if we think about, even the monitor I'm looking at today or the TV you're looking at or your mobile phone, we're actually looking at polymers every day with the OLEDs. Those are organic LEDs. And so we are different in terms of chemistry than an OLED. An OLED, you put a voltage or a bias and you get red, green, and blue light. You get enough pixels, you can make it into a display or a television. You put a voltage on our polymers, you can switch light, you can change the optical refractive index. And so the interesting performance attributes of using polymers is they have naturally very high bandwidth, both electrical and optical bandwidth. In fact, it's higher than you see in semiconductors. And what's more, you don't need a lot of electric field to change the refractive index. And so some of the polymers that we've been demonstrating quite easily perform at the data rates everybody's looking at today, which is 200 gigabits per second per lane, which is a data center type spec. But we're driving these things less than 1 volt. And so that's very, very low voltage. If you think about that from a architectural standpoint, if you're driving voltage levels or a volt or less, you don't really need to have dedicated driver chips. You can actually drive these things from the existing electronics, be it ASICs or DSPs, etc. And so you're providing not only an interesting path to higher performance, which is what the industry is just striving for right now, you're also allowing the power consumption to be down, as well as easing some of the electronics issues. And so there's a number of really interesting attractions of using polymers. But I think, from that standpoint, the material has lots of inherent advantages. Now, we design it into a slot modulator format, which is teeny weeny. And so it's really, really small, and which is ideal to shoe on into, the vehicle that data centers use today, which are pluggable optical transceivers. The other interesting thing is that this polymer material you make it into a liquid form. So you add a solvent to it, and you can literally put it into a normal silicon fab and just spin it onto a wafer, just like you do photoresist. And then you can photolith it just using standard techniques. You can dry etch it, wet etch it. You can put metallization on it. So what I'm trying to say is the integration into a silicon foundry is not that difficult. Some of the other more exotic modulator technologies certainly are having some issues there, but for us, this is a positive advantage. So you've got really high performance bandwidth, you've got low power consumption, no voltage drive, you've got ease of integration into a silicon foundry that's doing silicon photonics, and it's very small size. So one way to look at this, if you want to dig into the technical side of it, is silicon photonics is this great platform everybody's been talking about and has implemented. There's a number of companies that implement that into Datacom today. We're actually upgrading the performance of silicon photonics using our modulator technology that can be added to these platforms. And that's a real plus for the industry.
Now, I'd like to talk about some of the challenges with this platform. If there are any, and how you guys are addressing those.
Well, it's a new technology platform, and if anything, it's a disruptive technology platform. But what you have to be careful of when you develop in new technology platforms, you don't want to have the ecosystem be disrupted. So you want to have a disruptive solution that has much higher performance, for example, but you don't want to ask your customers to go redesign all the switches and the routers or all the pluggable modules. You want to be able to have it fit neatly into existing infrastructure. I call it the ecosystem. And that way, it's much easier for new technologies to get accepted. And so we've been very careful here to design our solution so it goes into the standard vehicles, whether they are optical pluggable transceivers or co-packaging solutions. Really what you're doing is you're upgrading the engine. And so whether, if you want to talk about cars, for example, a pluggable may have a 4-cylinder engine, and for us, you like putting in a V6 or a V8, so you're really upgrading the performance, but you're not actually changing the shape or the mechanical design of that transceiver itself. That's remaining the same. So it's minimum disruption in the ecosystem. But to go back to your question, what obstacles and problems have we seen? Of course, you've got a brand new technology platform. You're always going to have those. And so the first thing we always think about is if we're looking at polymers today from an OLED perspective, and that took 20 years to get OLEDs accepted as a display medium. I mean, we used to have plasma and CRT, and then we had LCD, and now we have polymers. It took a long time for the industry to accept the polymers were reliable. They were stable. And I, worked on OLEDs in the early days, and they weren't that stable, but they are very, very stable today. And we don't even think about that. And I think this is the same issue when you're bringing a new technology platform to market that has a polymer-based element. People are going, well, is it robust? Is it reliable? Is it stable? So we're actually at Lightwave really doing a lot of reliability, accelerated testing, lifetime work in terms of different temperatures, looking at different techniques, trying to really understand how robust this material is. And actually, we've been positively surprised. This is more robust than we expect, and we're really excited. So we're in the mode right now of conveying that to the industry. We're very happy with the performance. We see this as a long-term solution for the industry in terms of performance and how it can add value to the optical network. But those are the things we're working on really hard. And I think as you bring a new technology platform to market, and where either you've increased the performance or you've changed the technology itself, you've got to go through these things. And certainly we're carefully going through all of that.
Glad to hear it. In terms of the commercialization process, where is Lightwave Logic in that journey? Can you tell us about some of your recent developments?
Yeah, we can. So this year we demonstrated our technology, our material chromophore, we call it polymers, inside a slot modulator. Um, and I gave a presentation at the OFC conference, that's the Optical Fiber Conference earlier this year. And we were showing really world-class results in terms of what the industry was looking for next generation pluggable transceivers. That's the 200 gigabits per second per lane. And we're showing very nice performance at less than 1 volt. And so from that standpoint, we actually attracted a lot of companies because companies that were using silicon and indium phosphide now realize that with the drive of artificial intelligence to upgrade speed and data flow on the internet, because the extra computation that machine learning is generating, yes, there's a GPU chip, and yes, there's a lot of memory, and yes, we're sending lots of data within the chip. But there's also a lot of data that's getting sent off the chip. If it's getting sent off the chip, a lot of that data goes through a fiber optic network. If that data goes through a fiber optic network, that means if you've got a pluggable transceiver sending data from the GPU chip into that fiber optic cable to some destination, people are now wanting to upgrade the pluggable transceivers in terms of performance. So there's this real big demand to go from 400G to 800 to 1.6 terabit. Whereas if you think about this a year ago or even 2 years ago, we weren't even mentioning these numbers. But today at the conferences, people are talking about 3.2 terabits per second and 6.4. The challenge is what technologies are we going to use to support those increased data rates and keep the power consumption under control, both from an optics standpoint as well as an electronic standpoint. This is a big challenge. We have a technology solution that really addresses that. And so that's the exciting part about what we're doing in terms of putting the technology to market and getting commercial interest. Now, to go back to your original question, how is that commercial interest occurring since the OFC timeframe? It's been quite exciting, to tell you the truth. We've had all different types of companies. We're engaged in lots of discussions, especially the transceiver manufacturers. So these are large companies that are, from one standpoint, looking to integrate our material technology into modulated chips, to put the modulated chip into an optical subassembly as part of the transceiver design, as well as companies looking at our material and implementing our material into their silicon photonics line. So a lot of companies have their own silicon photonics foundry or line, if you like. And so there's a couple of different directions here that are generating a lot of interest. And that's exciting because we have a business model to support licensing and technical transfer of our polymer material to these types of opportunities, as well as putting material into slot modulators and selling the slot modulators into the transceiver environment. So if you want to look at it from two buckets, there's a lot of commercial interest in the material itself because we've had a lot of IP put in place, and we've had one license already, one commercial license already, materials license already put in place. And we're looking to increase that with some larger companies, as well as interest in slot modulator devices themselves. So I think from that standpoint, there's a lot of really good interest. I think if I stood back and look at this from a 20,000 foot perspective, the whole industry now realizes that they have to use faster optics, faster optical modulators for the solution going forward. I'm sure there's going to be electronic solutions. I'm sure there's going to be more encoding type solutions. But the industry has definitely all agreed that this is a market that they can't live without. So the market is real, the opportunity is real, and we're certainly seeing other companies with different technology platforms all jump into this market as well. So this is a really exciting time, all really being driven for the most part in the last 2 years by the GAI, the artificial intelligence drive to increase performance.
Excellent. It sounds like things are really getting rolling.
Yeah, this is definitely exciting times. Now, I don't come across as being too emotional, but when you have a market like this, these don't come along that often. When you've got this big drive, you've got the capital spend by the data center companies that actually is upgrading their equipment. As they're upgrading their equipment, they're saying, we need higher performance equipment. They're going to the component manufacturers and say, guys, we need better components here. And so the whole ecosystem, not only optical components in terms of modulators, but the electronics as well, is all being upgraded as fast as humanly possible. So yes, you're absolutely right. This is super exciting times.
Speaking of excitement, uh, in terms of this technology and your work, what is it that you find exciting about it? What keeps you interested?
So if you think about what I've been focused on in the last half decade, if you like, is bringing a new technology to market. I've done this a number of times. One of the most notable examples was VCSELs back in my Motorola days in the 1990s. Bringing a new technology platform to market is exciting. If we just think about VCSELs for a second, the vertical cavity surface emitting lasers, right? At the time in the 90s, the only market we could really see was short distance parallel optical interconnects. If you look at VCSELs today, they've been used in laser mice, they've used in structured sensing and all different types of sensors. I mean, it's just incredible how the VCSEL laser has just become so incredibly popular in terms of volumes of billions of units. Bringing that technology to the market wasn't easy. It was actually very, very difficult. And the same thing goes with bringing polymers to market, or electro-optic polymers. It's not easy. This is difficult. And you've got to get the customers to accept and trust a brand new technology solution. I mean, I remember back in the 90s when we were working on the VCSELs, the guys who were making the edge emitting lasers, the CD lasers, the 780s, said, yeah, VCSELs are never going to make it. CD lasers is where it's going to be. We're already in huge volume. And look what happened. We don't see 780s anymore. We see lots of VCSELs. So I think what we're going to see here is we're going to see polymers, and I've said this a number of times, become ubiquitous. It's got the performance. It's got the natural manufacturing advantages. It needs companies like ourselves to really bring this platform to commercialization. And the good news is we've structured the company. We're well funded. We're a public company. We don't have any debts. We have good runway. We have good investors. We have a world-class team. And these are the types of things you really need. And this is what really excites me. Brand new technology platform. It's going to really change the way optical networks are going to be driven in the future. And I'm really excited about it. And that's what keeps me awake at night.
Michael, thank you so much for your time. We really appreciate you coming on the podcast and speaking with us.
No, I really enjoyed it. It's been a great chat. Thank you.
Today's episode is brought to you by Avantes. Unlock the power of light with Avantes. For over 30 years, we've delivered precision fiber optic spectroscopy, trusted for custom integration and reliable data. Discover how to empower your application, industrial, scientific, or beyond. Visit Avantes.com and experience spectroscopy solutions that innovate. Today's episode is also brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical knowledge and manufacturing expertise to be your optics partner every step of the way. Visit lightpath.com to learn more.
Up next, our conversation with Steven Milton, Vice President of Accelerator Science at Tau Systems. For those in our audience who might not be familiar with your company, could you give us a quick overview of Tau Systems, the technology space that it works in, and what its goals are?
Yeah, thank you, Joel. I appreciate that, and I appreciate the opportunity to talk today. Tau Systems was formed roughly about 3 years ago by Michael Lebby. He's a professor at University of Texas, Austin. He had been doing work for the past decade plus on a topic called laser wake field acceleration. Laser acceleration's been around. The idea, the concept has been around since roughly 1997, when Tajima and Dawson first came up with the idea. And I'll get into a little bit more detail about how that process works a little bit. But fast forward, a number of decades, and people have had the opportunity to explore how that system works, but most importantly, develop the technology to actually see it through and make it exist in reality. Most importantly, the laser systems that are used to drive it. So the laser wake field accelerator, you need a laser. The interesting thing about it is, its capability of generating particle beams. In particular, we're most interested currently in the generation of electron particle beams, and not just ordinary particle beams or ordinary electrons, but very, very high energy electron beams. And what I mean by high energy electron beams, where we accelerate them. So it's like a particle accelerator. It's a miniature particle accelerator. And I've been in the field of particle accelerators since roughly 1980, so it's been a while, and I've been watching the development of the laser wake field accelerator since its inception. But we've reached kind of a point in that development, in that technology, where one could actually commercialize this device. And again, I'll get into some of the specifics in a second, but the commercialization of it, and the ability to bring it out, we are the very first company to do this with this system. So our concept is to bring very compact, high energy particle accelerators to the commercial sector for a variety of applications. And that's what the initial genesis of Tau Systems was, is to capitalize on this unique transformative technology, or transformative technology, and bring it to the commercial sector for, like I say, a wide variety of applications.
So now, when we think about an X-ray free electron laser or a particle accelerator, typically we're not thinking of something small. These, traditionally speaking, are very, very large machines. How does one go about shrinking them down?
Well, you put them in that little oven, and you turn that lamp on, and they just go like,
right, shrinky dinks. Yeah,
exactly. No, it's actually, it's more interesting than that. And this is kind of where the fun begins, in a sense. Particle accelerators have been around, for since the early 1900s. In one variety, shape, or form, and then developed quite rapidly with the advent of radar technology and the development of high power radio frequency systems. And it was the physicists who decided that we can use these to generate very high voltages, potentials to accelerate particles through. And this was done back, like I say, in the 30s, 40s, 50s, etc. And as things grew, the capabilities of machines continued to grow, and yet at the same time they continued to get larger and larger and larger. And we tend to define our machines and particle accelerators by a metric, and that metric is the gradient. So the volts per meter, or in our case, megavolt per meter. So millions of volts per meter types of gradients. Particle accelerators tend to be in the few megavolt per meter up to tens of megavolt per meter. You will hear some people talk about particle accelerators that are capable of 100 plus megavolt per meter, but these tend to be very small. And even if I wanted to generate 100 million electron volt beams, in 1 meter, I still need a fairly large and powerful RF, or radio frequency power system to generate that type of capability. The laser systems, however, have come along and have changed things. So, in the particle accelerator world, one of the things that limits the technology is just the field itself. If I try to generate a field, I need to put it into something that looks like a copper structure, let's say. I make a resonant condition, I build a field up. Eventually the field becomes so high that the materials start breaking down in the copper. It starts sparking. I get arcs and I damage the structure. And that's what limits the field gradient that one can get in a particle accelerator, is that system. Similarly, on a kind of another scale, when it comes to repetition rate, things just heat up. You put a lot of power in them and they want to heat up. One of the other advent, changes that have happened in sort of standard particle accelerators is the addition of superconducting technology. And so there are superconducting accelerators out there that can get very high repetition rates, but the gradients tend to be lower. They tend to be on the order of tens of megavolt per meter. So if I want to generate 1 billion electron volts, all of a sudden these things start becoming longer and longer and longer. If I want to get, so that's 1 GeV, we will call it 1 GeV, 1 giga electron volts. 10 giga electron volts, now this, if I'm at, let's say 30 megavolt per meter, 3 meters is 100, roughly 100, megavolt. I need to go, 30 meters to get to a GeV. I need to go, 300 meters, and then there's the fill factor, and all of a sudden these things become monsters. The laser wave field accelerator, the way it functions is immediately we take a laser, we send it through a gas, and we strip all the electron stuff. So we just basically don't have to deal with structure damage. The structure is a plasma. And by doing that, you now don't have to worry about, like I say, the damage issue. You can get extremely high gradients. And when I mean extremely high gradients, I don't need a gradient that is 10 times more than conventional or 100 times more than conventional, but 1,000 times or perhaps even more than conventional accelerator. So now when I want to generate a 10 GeV beam, as opposed to going, a kilometer to do this, I can do that in 10 centimeters. And in fact, Tau Systems and the people within Tau Systems, and Manuel Hegelich, we have a paper out. We now hold the world's records for acceleration in a laser wave field accelerator of 10 plus GeV and basically a 10 centimeter length. So it's a game changer. And I tend to, I guess the way I tend to phrase it is, whereas conventional particle accelerators have had a long history of development, and they're evolutionary, and that evolutionary path tends to be slow now because you can only change so many things, and you have to grow, and we understand things. The laser wave field accelerator is a revolutionary technology. It's not just an evolutionary it's revolutionary. And we can now shrink things down to a very small distance to generate that electron beam compared to the conventional systems. And that's what makes it extremely exciting, and brings it to the forefront, and why we are doing the commercialization of the system.
Absolutely. Now, looking at your technology platform, I'm sort of reminded of an early quote about the laser, which I'm going to paraphrase. Somebody said something like, "It's a solution looking for a problem." And that quote doesn't really fit here, because we do know a lot of problems that this technology would be really good for, because we've had these massive unwieldy machines for quite some time now. But, because they're so huge, they're so hard to build, there's not very many of them. And, the people who get time to experiment, as I understand it, they can't really do so indefinitely. So, it seems to me that there's this huge realm of possibility that has yet to be explored. What would it mean to increase the availability of these machines?
Yeah, that's a great question. And I have to say, it's more than just experiments. If you look at, accelerators themselves, clearly they've had a major impact in science. I think there's a statistic out there, which is kind of an interesting statistic, is that 1/3 of all physics Nobel Prizes, you can tie back to a particle accelerator, which is, it just shows you their huge, impact, on the world and on science. But there are also, tens of thousands of perhaps even more smaller particle accelerators out there in the world, doing, a wide variety of things, whether it's, a particle accelerator that's, very mundane, in the dentist office, generating x-rays to sit there and take, an x-ray of your teeth, or whether it's, proton therapy systems for cancer treatment, or one of the reasons why our tires last so long on our cars, because they've been treated with particle beams, and there's a wide variety of things that are industrial applications, defense and security applications, environmental applications, etc. So it's more than just experiments. So being able to increase their availability, means being able to do more than just the R&D. But if I focus back on the R&D, the capabilities of exploration, as you pointed out, these machines, the user being able to get time on these machines, it's precious on some of these machines. Very difficult sometimes to get that time, and that tends to mean that many times you get people, that will make the proposal to do an experiment that happens to be a proof of principle type of thing, as opposed to trying to further, a deep understanding, or trying to be more risk taking on the type of experiment that they want to do, and exploring things in a more complex space. If you have that tool widely available, people are going to be willing to say, well, what if I put this in here? What if I try that? As an example of where I think that there's a lot to be learned, and if I look at, scale, I look at the atomic scale, right? The little atoms, et cetera, molecules. Things behave in a very, quantum physics type of way at that type of scale. However, if I, take a whole bunch of these atoms and I put them together and I make a big metal bar out of them, that bar is now, macroscopic, and it has its own types of properties that aren't really particularly quantum mechanic when I look at it. There's a difference. There's a space in between there, the mesoscale space, where grain boundaries matter, and how did I make that piece of metal? Did I forge it? Did I cast it? How did I put it together, and why are there differences? And understanding that mesoscale at the grain boundaries and the interfaces for things such as batteries, for instance, is hugely important. And being able to have more machines out there that have that ability, that capability of exploration, would be a tremendous success for science. But then if I take it to the industry side as well, the type of beam that a laser wave field accelerator can generate is in itself somewhat unique, and it has certain properties that other machines just won't have, and it's also on a very compact scale. And you now start opening up, because of that compactness and that unique beam capability, application space in industry that is hugely important, that wouldn't have been there before. And being able to develop those technologies into true applications that sit on the floor of industry is important as well. So I think that by the ability to shrink these things down so that one can, afford them, and utilize them in a small enough space in both industry and in discovery science, is what we're aiming for.
Going through the Tau Systems website, there's all these very big, very bold claims that might be kind of easy to dismiss as a layperson, or maybe as a potential investor who doesn't really know the types of research that are enabled by these very large laser accelerator systems that we've had for the the better part of the century, and have been developed over that time. I'm curious how you approach those sorts of conversations. With a lot of high-tech startups that we cover, I imagine it's pretty hard to convince people to invest, to be able to explain your concepts. But with something like this, I imagine it might be a little bit harder, or maybe it isn't. How do those conversations go? And what does the pitch look like? And how do you keep that conversation grounded?
Yeah, the answer is somewhat basic in a sense. The concept of the laser wake field accelerator, as I pointed out, has been around for quite some time, since '79. I mean, there is no mystery there about the fact that these things actually do work. There's and what I found very interesting to me, back a few years ago, was the fact that people were starting to write papers and starting to move away, not from the development of the laser wake field accelerator itself, but to the application of those beams directly from that laser wake field accelerator. And those applications are very much in line with the typical application that you might find for many of the other particle accelerators out there in the world that already have a very established user base. So if one starts from that point, saying, listen, we are developing a technology that, will cover that same space, but, its capability, its compactness, its price point is going to be significantly smaller in both sense. You're already kind of grounded in a proper area right there. The system itself, however, it still does require, it is a new product. It does require development to put it into a package, I suppose, that is capable of supporting a user program or a industry for that matter. And the process itself, driven by these now just so I should have pointed out, one of the things that really has enabled the laser wake field accelerator has been the tremendous progress in laser technology. It was only wasn't that long ago when people started talking about terawatt laser systems, and then tabletop terawatt laser systems, and then tens of terawatt, hundreds of terawatt, even petawatt laser systems. And the technology has grown, the efficiency of those systems has grown, the repetition rate of the systems, and that's really one of the enabling technologies. And that's a very robust sector of the market out there when it comes to laser technology. And that's another reason why we believe it kind of grounds the ability of using these things. But the product coming out, certainly is the electron beam coming out of the laser plasma itself. But immediately you have extremely high brightness X-rays coming out that are also of huge value when it comes to imaging, or 3D imaging for that matter. So you get what we're called betatron radiation coming out of these devices. It comes out from an extremely small spot. If you think of a pinhole camera, your resolution is limited by the size of that pinhole. Well, our spot sizes are limited to the size of our beam coming out of that laser plasma radiation sector or volume, and that's on the order of a couple of micron in size. So you all of a sudden get extremely high resolution and very, very high brightness beams. So our plan, our path is to generate a laser wake field accelerator in a robust package, immediately use the product, which is the electron beam and or the betatron radiation, directly for applications where we already have identified a customer base, already have interest in it. And then at that point, because these are really, like I say, ultra short pulses, these pulses are less than, they're in the order of tens of femtoseconds in duration, ultra small when they come out. We can use those directly. But at that point, we can use them for radiation testing, for instance, of electronics. We can use them. We have customers for that. We have a contract to do that at this point, to work on the development of that particular system. And then to move on to then tailoring the electron beams as they come out for other applications. And then once we've done that, go to that next level of, for instance, doing the free electron lasers. So it's a step-by-step process where we are saying immediately within the next year, we will have a product. We are bringing in actually revenue already currently for the development of the radiation testing system. Get that out to customers, build on that one, and then add the next layer of complexity and the next layer of complexity, all the while building on our initial core capability, which is that laser wave field accelerator.
Now, you've already sort of touched on this a little bit, but I wanted to see if you could go into it just a little bit more detail and maybe describe some of those applications that you've mentioned. But in terms of the path toward commercialization, where is Tau Systems in that journey? Can you tell us about some of the recent developments that you guys have had as a company and some of your near-term goals?
Yeah, our plans, so currently we have a development and application center that we are building up in Carlsbad, California. It's roughly 24,000 square feet. We have the laser system, the first part of it already installed in there. We are building up over the next year, the radiation vault for the accelerator system and additional laser rooms for laser development. So we plan on having a functional electron beam in 2025 in the Carlsbad facility, where we will be focused on initially on the radiation hardening testing of electronics for space applications. That's a big topic right now, and it's one of our, like I say, our initial contract is for the development of a system for exactly that purpose, to not only supplement, but to some degree display, and make it more widely available, the ability to do what is called single event effect testing of electronics, which, fly on rockets out into space, because there's a lot of radiation out in space, and someone needs radiation hardened electronics. So that's one of the major things. We also have a system that's up and operational at the University of Texas at Austin. That is where Manuel Hegelic is also not only CEO of the company, but also professor of physics at UT Austin, where we are testing out the development of radiation testing systems. We're also doing the Betatron radiation testing there, and we also have got some work that we are exploring on medical applications on the system there. We also have a contract with the Lawrence Berkeley National Laboratory, where we, because we didn't have initially a full free electron laser system at hand that was driven by a laser wave field accelerator, but they happened to have something that they were working on. So we joined up with them, and we already have some very interesting results that we've done on that collaboration. So we've got a multi-pronged development path, but we plan on, like I say, having built the radiation test center for beam time for customers in the 2025 range. We hope that by 2027 we'll be leveraging our systems to be able to do 3D metrology of computer chip designs, because that is now, as the computer chips become smaller and smaller and they become more and more 3D, there's a lot of interest on how does one characterize these things? How does one, perform the testing, the metrology of the 3D chips? And that will be in roughly a 2027 timeframe. And then we just continue to build our product further and further towards our free electron laser plans that we have off in the future that, one day could be used, for EUV lithography and for chip fabrication, for instance. So that is the long-term vision, but we have a long-term vision, but we also have, like I say, the short-term roadmap, I suppose, step-by-step process up to achieving our long-term vision.
Now, as a final question, I've been asking this recently just because I feel like it kind of gets people excited, it gets people talking. What is it about this work that keeps you interested? What do you love about it?
Despite some of the things I've said, we still don't know everything. And I'm always joking with Manuel Hegelic, about the fact that, that laser system, that drive laser system up front, I understand that, very well. The electron beam transport system downstream, I understand that really well. But this little volume of, roughly a centimeter in length or a couple of centimeters in length, still is while we can make the system work and we've got a very good understanding of how it works and we can generate beams, there's still a huge amount of potential there. There's a huge amount of the ability to be able to test new concepts and new ideas and make this even better. I think we're just at the beginning. I've been in the field of accelerators since, as I said, roughly 1980. So it's been a few decades that, I've worked on accelerators and I have a fairly good understanding of how they function, et cetera. And I've seen the progress over the years and the evolution. But this technology, as I said, is revolutionary. And we are just on the tip of being able to like you say, we can commercialize it now, but we can do a lot more with it, I think. And that's what I think is exciting is that ability to not only have something that immediately shows not just promise, but applicability. And yet looking at it further shows a huge amount of additional potential well beyond what I think we even understand about it at this point. And that's what I think is extremely exciting about the whole concept and why, in fact, one of the reasons why I joined the company and said, okay, I'm done with the conventional accelerators. Let's go off to the future and let's get rid of the horse and start, driving our cars.
Excellent. Yeah, you've got to be excited about just the sheer possibility of what's going to happen when these systems are kind of out in the world.
Yeah, and I am, and then that's the whole thing, and I think it's very exciting that even in as short term as next year, we plan on having a device available for our customer base to use as a application center in Carlsbad. So yeah, we are making it real when it comes to putting a laser wake field accelerator system out there for commercial use. And that I think is also, when you get to do something first in the world, it's always fun.
Thank you so much.
Hey, my pleasure.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.